Good afternoon, everyone. My name is Ricardo, and I'm a student at CRCT. Today, I'll be presenting some simulations regarding the production of titanium using FaxH. So here's a list of some of the points that I'll be presenting today. First, we're going to start with a brief introduction. After that, I'm going to introduce the reaction module of FaxH, and we're going to study the direct carbon reduction of titanium dioxide. We're going also to look at the documentation section, and after that, a series of simulations mainly in using the equilibrium module of FaxH. So for the application of titanium alloys, they are classically used in airplane applications, so mainly in aircraft engines and landing gear. But recently has been reported that the chemical industry has started to use these alloys, and this is because they use oxidizing acids. So for those cases, high corrosion resistance is required. Regarding the raw materials for production of titanium, we have different ores. The two principal ores are ilmenite-based and rutile-based ores with different compositions or concentration of titanium dioxide. Uh, Overall, ilmenite was the most important and accounted for 91% of the world sulfur for titanium in 2011. Well, it is also possible to obtain a synthetic rutile, and this can be achieved by eliminating iron oxide and other impurities for ilmenite. So in this work, we're going to be presenting the simulation starting from rutile, which is already integrated in the FaxH database. So now, starting from rutile, which is mainly titanium dioxide, we want to explore the pyrometallurgical processes that are required in order to produce titanium. So during this workshop, we're going to answer some questions. Some of them are: it is possible to obtain titanium from direct carbon reduction of titanium dioxide? What would be the operational temperature? It is preferable to produce titanium in the liquid or in the solid state? And also, what other processes are required to produce pure titanium? So let's begin by exploring the direct carbon reduction of titanium dioxide, and this will be carried out by using the reaction module of a FaxH. So this is the FaxH main menu, and in order to investigate if it is possible to produce liquid titanium by direct carbon reduction, we're going to start by using the reaction module of FaxH. We have here our first reactant, which is titanium dioxide. Now we can add the other reactant by clicking here. We know that we need 2 moles of carbon. The next step is to add the products. So we can add the products by clicking here. So we want to produce liquid titanium. And we also know that as a product, we will get 2 moles of carbon monoxide. Now we click on next. And we can start by exploring temperature. So in here we can start by 1000 Kelvin up to 3000 Kelvin by steps of 100 Kelvin. We click on calculate, and we can see that this reaction starts to be spontaneous, some in a temperature between 2000 and 2100. So to know the actual value, we can just erase this, clear the calculation, and now we can impose the delta G as 0, which is Gibbs free energy. We click on calculate, and now we know that the theoretical temperature for this reaction to occur is around 2040 Kelvin, and which has the enthalpy of around 700 kilojoules. So to answer the question, it seems theoretically that it is possible to produce liquid titanium from direct carbon reduction of titanium dioxide. However, we can see that this is a really high temperature for this endothermic reaction, and this may lead to refractory material challenges, so in practice is not suitable. So as we noticed before, we needed a really high temperature in order to produce liquid titanium. So now we need to answer the question if it is possible to produce titanium in the solid state by following also a direct carbon reduction. So now in the reaction module, we're going to change the state of titanium. We click on solid. We also want to explore different pressure conditions. So this is why now I'm going to select non-standard state. And now we're going to put pressure as a variable. We click on next. So now we also know that the melting point of titanium is around 1941 Kelvin. So we can imagine by imposing an operational temperature of around 1400 Kelvin. And we're going to impose as well the delta G as 0. We click on calculate. And now we can see that the pressure is around 7 Pascal. So to answer the question, we can see that it is theoretically possible to produce titanium in the solid state. However, these high vacuum conditions are really difficult to apply in practice. So now we're going to take a look into the documentation section of FactSage, mainly to see the melting of titanium dioxide. The documentation is found in the database section of FactSage. So for example, here by clicking documentation, the user can look for the compounds or system of interest. This is important because in this way, the user can confirm if a system is already integrated in a database and it has been optimized. So for example, here we can see that titanium dioxide is already integrated in the FD oxide. So by exporting these kind of phase diagrams, we can obtain valuable information. So in this case, we can observe that rutile will melt into a slag phase at around 1850 degrees Celsius. It is important to point out that the reaction module only considers stoichiometric compounds. So now in order to see the formation of other compounds or other phases, we're going to rely on the equilibrium module. So this module will indeed allow us to see the more accurate partitioning. Now we're going to export the equilibrium module of FactSage. So from the reaction module that we explored before, we have the operational conditions to produce liquid titanium and also solid titanium. So this equilibrium module has a better prediction of the phase assemblage or phase partitioning. And for example, in literature, it has been reported the formation of titanium carbide by direct carbon reduction. So we're going to test if FactSage is able to predict this compound. So this is the interface of the equilibrium module. So the first step is to put the reactants. As you can see, I started by pouring 1 mole of titanium dioxide, and I'm going to make it react with carbon. As you can see, I'm putting alpha in the quantity of carbon, and this is because it is a variable, and I want to vary the concentration of carbon to see different scenarios that can happen during the carbon reduction. So the next step is to select data search, and here we're going to select the correct databases for our simulations. So for example, here we're going to select FactPS in order to account for gases and stoichiometric compounds. The next one is FD oxide, which will account for the formation of slag phases mainly. And finally, we want to select the FD light database. And this is because we're going to use magnesium at some point of the simulations. So the next step is to select the menu window. So now here I'm going to select all the gas, pure solids, and also I'm going to select all the phases. So as you can see here, I already started putting values of the alpha parameter, and I'm going to make it vary from 0 to 3 in step of 0.01. So I'm putting these specifications because I can see three different scenarios. That is when carbon is less than 2 moles, I can see the effect of carbon deficiency. At 2 moles, I have the stoichiometric amount, and more than that, I have an excess of carbon. So as we noticed before, for production of liquid titanium, I already set up the temperature here and also the pressure. So now I just click on calculate. So this is what we get as results. By taking a quick look into it, we can see that even for carbon deficiency, there's already the formation of a slag phase, which is not desirable. So if we go to the next page, we can see even for carbon deficiency, there's formation of the slag phase, and also at this point we can start seeing the formation of the titanium carbide. So now in order to see the effect of carbon more clearly, I'm going to plot the results. So in this option, I'm going to go to axis. In the axis, I'm going to select alpha, which is the amount of carbon at the x-axis, and the y-axis. I'm going to plot different species. And so I'm putting also mole, but these options can be modified by selecting the axis of interest. So now we're going to select what we're going to present in our plot. So we can click in here, select, or as you can see here, I already started selecting some faces. So I'm going to show first the moles of titanium in the titanium dioxide. Also, I'm going to present how many moles we have in the slag phase. We are going to report the moles of titanium in the titanium carbide, and also the carbon in this phase as well. And finally, I'm just going to present the amount of the moles of carbon monoxide. Here we just go in plot, and with this what we got as results. Now this graph can be modified to make it look nicer. So as you notice here, I'm going to run in parallel the simulation for the production of solid titanium. So the phase selection and stoichiometric compounds is exactly the same as before. Now we're going to change only the temperature, which was 1400 Kelvin, and also the pressure of 7 Pascal. So as you can see, I already saved this file as solid titanium, and you can see in case you want to reproduce the results. And I also saved the file for the liquid production. You will find the names here below. So now I'm just going to calculate as well, and the steps for the plot are exactly the same. So by taking a look into the results for carbon deficiency in the production of liquid titanium, we can see that all the titanium goes into the slag phase. After that, at around 0.4 moles of carbon, there starts the formation of titanium carbide, which is the blue line. And we can see that for the stoichiometric amount, which is 2 moles of carbon, there's no formation of liquid titanium, and all of this goes into the titanium carbide. And after that, even for the excess, we only see titanium in the carbide. So now by taking a look into the results for production of solid titanium, we can see that there's no formation of the slag phase. This is because we lower the temperature. However, titanium goes into different oxides, and overall it's the same trend. So as we can see in the blue line, most of the titanium goes into the titanium carbide, but there's not production of solid titanium. So now to answer the question, is titanium carbide forming? So yeah, it is forming, even though if we target liquid or solid titanium, we ended up by forming titanium carbide. So it's not possible to produce it with direct carbon reduction. Now we are going to use an auxiliary element, which is chlorine, and now we're going to study the process of carbon chlorination roasting. To account for the correct phase assemblage, simulations are going to be carried out again into the equilibrium module. So from here, simulations are going to be carried out based on the parameters that were found on literature, and mainly for the crawl process, which is one of the most important process for the production of titanium nowadays. As you can see, we start from titanium ores, and as a result, we can obtain a titanium sponge. So now from the crawl process, we're going to start with the carbochlorination roasting. So the main advantage of using this step is that by playing with the affinity of chlorine, we can transfer titanium and form TCl4, and then this gas can be treated after. So in this window, we can put all the reactants again in the equilibrium module, and now we click on next. So as you can see now, I'm selecting again all the phases, all the solids, and all the gas. Also, it is important to point out that here we are also selecting the pure liquids because we don't have an extended database for the simulation process. We can see that FraxStage is able to predict the TCl4 formation and carbon monoxide, along with a minor addition of other components in the gas phase. So now the next step we can think is the reduction unit, so we can perform the magnesiothermic reduction of TCl4. So here the magnesiothermic reduction is going to be performed using the equilibrium module as well. So now from the results of the carbochlorination roasting, we can save the gas phase. To do so, we go into the results and then we click into output, stream file, save gas phase. So now we can import our stream, which is a red arrow in the diagram. To do so, we go into the equilibrium module, we go into edit, mixtures and streams, import a stream, and then gas phase, which is the one we just saved. So once we have imported our gas phase, we can add the magnesium, and we're going to add again an alpha parameter to see the effect of its concentration. So again, I'm going to select the gas phase, pure solids, pure liquids, and all the phases. And also, there's another way to simplify this problem. So if you remember correctly from the results, we obtained the mole fraction of the gas phase we obtained. So by accounting just for 1 mole of the gas phase, we can consider 0.33 mole of TCl4 and 0.66 mole of carbon monoxide. So then we can now make vary also the amount of magnesium. So I'm going to put it as an alpha parameter, and it's going to vary between 0 to 1.4, and the temperature and pressure were taken from literature for this process. So the results are presented in the figure here. These results are important because they will let us know if we can just take the gas phase coming from the carbochlorination and then treating with magnesium. But however, as we can see in the results, there's again the formation of titanium carbide. So the answer to this question is no, and that is because the presence of carbon leads to the formation of titanium carbide again. So we need to do some process before proceeding with the treatment with magnesium. So the gas phase needs to be treated before coming to the reduction unit. To do so, we make a condensation. So this is to remove the CO, and also a distillation is needed to remove the excess of carbon that can be in the gas. Now that the gas has been purified, it can come to the reduction unit. And this is why we can see in the crop process there's a purification part that was needed. So by following the steps of the crawl process, now we can pass into the reduction unit. So as we discussed before, by 1 mole of a gas obtained from the carbochlorination, we obtain around 0.33 moles of the TiCl4 gas. So now we're going to make it react with the magnesium. This is why I'm putting here magnesium as an alpha parameter. As we can see in the next window, I'm going to make vary this alpha parameter between 0 and 1. And for temperature, I'm going to take the temperature reported on literature for this process, which is 1273 Kelvin. one bar, I'm going to select all the gas, all the solid, liquids, and all the phases. It is important to point out that under those conditions, MgCl2 can dissolve GiCl2. So for this simulation, we're going to present two scenarios. The first one is without considering it, and the second one is we're going to make an ideal solution that is possible to make into FACSH as a first approximation. So to do so, we can go into pure liquid and do right click. Then we can put a right click again into the compound of interest. After the right click, we select ideal solution and ideal solution number 1. Then we accept the specifications as by default, and now we repeat the same procedure with MgCl2. The results are presented in the figure for the two scenarios. The thick lines are the results without considering the formation of a solution of MgCl2 and GiCl2. And the thin lines are the ones considering the ideal solution that we implemented in FACSH. So as we can see, there's no major impact in the production of titanium in BCC, because when the concentration of magnesium reaches the stoichiometric amount, which is around 0.63, there's the formation of the titanium sponge, so at the exact same composition. As we can notice here, after the stoichiometric concentration of magnesium, that is 0.66 moles, there can be an excess of liquid Mg and also an excess of liquid MgCl2. So this is why we need to do a treatment of the titanium sponge in order to eliminate this. So in here, the distillation of the titanium sponge is going to be carried out again in the equilibrium module. So before proceeding to the crushing of the titanium sponge, we need to eliminate the excess of magnesium and MgCl2. So by taking a quick look into the phase diagram of Mg titanium, we can see that we have the advantage that those elements are not miscible. So now, by keeping the same database selection as before, we can add the reactants. As you can see, I am supposing that for every 95 grams of titanium sponge, there's 5 grams of liquid Mg that are in the pores of the titanium sponge. So I'm going to run a series of calculations by varying pressure and also by keeping the temperature as the same as before. As you can see here, I'm selecting all the gas, all the solids, and all the phases again. So again, by following the same steps, we can plot the results. Here you can see that I perform different calculations with zero amount of argon in the environment and a maximum amount of argon of 7.5 grams. As you can see, when we don't have argon in the environment, the vacuum conditions are really exigent. So as I start adding argon into the environment, the vacuum conditions are less exigent. And for example, when we have 7.4 grams of argon in the environment, we can see that the vacuum conditions are only of around 0.87 bar. So finally, I repeated the same experiment, but now I'm adding MgCl2 in the liquid that is dissolving into the pores of the titanium sponge, and we see the similar trend. When we have no argon in the system, we need really high vacuum conditions, so the system needs to be really close to zero. However, as we start adding argon into the environment, the vacuum conditions are less exigent, and for an amount of 120 grams of argon in the environment, we can see that we could be able to evaporate all the liquid for pressure in the environment of around 0.8 bar. So this is how I conclude my presentation today. Please let me know if you have questions, or you can find in here my email in case if you want to reproduce the simulations and you have additional questions. Thanks.